Hello, everyone. Thank you all for joining us. We are in the decision-making session, decision-making and reasoning. We have a lot of excellent papers in this particular session that I'm very excited for. The way the timing is going to work is that there will be 10 minutes for the talks, 2 minutes for questions. We'll try to balance Slido and in-person questions. If you have a question, run up here. I'll put the microphone here and we'll try to get through those. If you're very shy, you can raise your hand and I'll run over to you, but we can cycle through these more quickly. That would be awesome. You can also post your questions on Slido as well, and we will try to collect those. All right, so we're going to jump right in. The first talk that we have is from Kashmir and Claudio. And if we could cue up the slides. Perfect. I'll let you take it away.
Okay. Thank you. Hello and good morning, everyone. And also hello, not maybe good morning to all the online audience. My name is Krešimir. I'll present our work done together with colleagues of mine, Manlio and Claudio from Argentina or Colombia, Sanyin from VRVIS in Vienna, and Meister from TU Wien, who sits here as well. So it's about analysis of ergonomic risk assessment. Today, the ergonomic risk assessment becomes more and more important. People are aware that it's important that workers, that people who work, that they do it in a healthy manner, that they don't do, they get injured, because for their well-being, but also to reduce the costs then because they will not be able to work, they will have to take medical care and so on. Still, traditionally, it's still done mostly with pen and paper in a very conventional way. The key to ergonomic risk assessments are the angles of the body parts. You can see here on the right, this is like various postures of the trunk, of the legs, of the neck, and for each angle or angle range, there is a value which will then be assigned. And people sit there and do it manually. Developments in computer vision allow us now, and in automatic analysis and machine learning, that we can easily extract skeleton from video, and in this way we can also compute the angles of the joints. So there is no need basically that someone sits and estimates the angle. We can record it and do it. The problem, or not the problem, the challenge is then that we have a lot of data, and as visual analytics has been deployed in many cases where we need analysis of complex data, we then decided to merge these two. So, and we here present Ergo Explorer. This is a visual analytics tool which is used to analyze ergonomic assessment data. Basically, this was developed in a close collaboration with domain experts. We had a lot of sessions with ergonomists, and we tried to here provide a tool which they could use to analyze a lot of data, a lot of angles, because we record the angles on the fly. We record the video of the worker doing some action, we extract the angles, and then suddenly we have a lot of them. And you will see why we argue it's better to have a lot of them at once than to have only one, which someone takes with pen and paper. Ergo Explorer is based on this task abstraction and requirement specification done together with the experts, and we deploy according to multiple views system with many views. I will not go through this slide. This is just that you see how many tasks did we extract it together with them to different types and different levels. And from these tasks, we developed 10 requirements which our tool should have. So the details are in the paper, so if you're interested in this task and the requirements analysis, just check the paper for the details. This is now their current state-of-the-art, so-called REBA table, or Rapid Entire Body Assessment Table, which they manually fill in during the session where they observe a worker. Oops, sorry. You can see these tables here, for example, on the let me find here. you have these tables, and you can see, for example, the neck can have three different angles. They look it here. If this is in this range, this is +1, +2, +2. And if it goes like this on the other way, this is +2. Leg postures, they have all these values, and they simply cross one field, and then they see where it is. So, and if you look here, if neck is 1, and leg is 1, 2, 3, 4, and then trunk is one of the 5, they find corresponding place, and they know what's the score for the first table. There is a score for the second table, the combined score for the first and second table, and at the end, they get a single number which describes the quality of this posture. They do have these tables, they're used to them, so we also made a table interactive in our view. This was quite important because they are used to it, they want to have it. We talk to them if this is the best way, but they are used to it and say, and here we don't have only one check mark because they do it one check mark, because they observe one posture, but we have all possible postures that are extracted from this video entered here. So you see here, for example, neck. This is the distribution of position 1, 2, and 3. And then for each of the neck positions, we have 4 leg positions. And then we have here these 5 trunk positions. And we here highlight, these are the scores that are assigned. And then we highlight as a heat map, we use color to see which is the most often posture. So here we have basically trunk number 2 combined with neck number 3 and leg number 3. This is, they can analyze which postures are most often in this series of images. The next, what we designed as a view is ergo gauge. And this is because angles are important. You saw that they have these angles. And we then here show in a radial layout all angles from our session. And we also here depict the values which they have in this table. Is it a good angle, bad angle, and so on. So they can see the distribution, how many angles are in which range. Here, there is no clue of time. This is just all angles summed up. This is for one joint. And on the top row, we have for several joints, and then they can see the values. And we can different mappings. We can also show something like this, that are not so critical. They don't go to the end. The others are longer and so on. So to tell them apart easier, or we can color code them to see which are in good range, which are bad range, using a traffic light metaphor. We know this is like red and green is not optimal for visualization, but they wanted like traffic light metaphor because it was easier to them to understand, to say, okay, we see red is bad, yellow is middle, green is good. We have this stripe of gauges for the angles, and then we also put this drawing or icon of a human body, and then just to be clear, which we do right, left elbow, left shoulder, and so on, but we also draw this connecting line so that they can orient themselves faster. Once they learn what is where, they learn it quite quickly. Interestingly, first we put this icon facing from the face side, but then the left and right is wrong, so we just turn the image around. We also have a timeline. This is with time. You can select angles. For example, here is elbow left and right. And then you can see the angles of left and right elbow over time, one in green, one in red. And you can see that sometimes the both elbows have the same angle, and sometimes they go apart. They are different. And this is exactly what is our point. They can analyze data in such a way. They can see if worker, for example, if he does wrong posture with elbow, maybe he also does it with a shoulder. But it's hard to see because they are focused on individual joints, But once you have the whole picture, you have all data at once with time, you can easily compare them and see if there is some kind of correlation that is unexpected. Here you can see the shoulder, and you can see this peak, how the both shoulders change the angle. They align quite well, and by elbows we have some differences. We can also do this on top of each other, of course, or several at once. And we can also use the color in the background to indicate which angles are green, which are red, which are yellow, so that they can immediately see if here everything is red, this is not good. Here we have some greens and reds and so on, so they can analyze this, what is happening with this. Of course, we do support interaction, linking and brushing. All views are linked, and it's easy to select something. In the table itself, they can just simply click on one of the scores, and then they see all others will be highlighted in all the views. So this is easy to. Okay, sorry, I'm running out of time. So what did we learn? Tables are important because they are used to it. This easy selection is essential, that the easy brush in all possible views, that they see it as they want. And this is the first thing we did. And we see there is still a long way in front of us until it gets widely deployed. You can see more details in the paper. Thanks for your attention. And now, if you have some questions.
Excellent. What questions do we have for our speaker? Any? Okay, I'll take one. I thought that the angle diagram that you had was really interesting. Did you find that there were some angles that were impossible, and so you had to utilize more of the certain portions of this diagram given joints?
No, because there are physical limitations. The elbow, you can't do it like this. Yeah, mm-hmm. I mean, if you would have like angle wrong in elbow, it would mean either you have a severe injury, mm-hmm. or the algorithm is wrong that extracts the joints. Mm-hmm. But we just use these possible angles, and this is also you can see it in the top view that the circles are different. Because you can't do all the angles. You can't also do your neck further than some physical limitations. With different joints, a different angle range. So, and we depict this outer circle shows you this physical range due to anatomy.
Excellent, that looks really great. Yeah. Any other questions we have for our speaker? Anything on slide? No? Okay. My other question was about actually this view here. So for an analyst, I think it makes sense allowing them to map the left to right and so forth. I'm wondering if someone is a doctor or practitioner trying to speak to a patient, if it would be useful to have it the other way, given they're speaking to a person that is in the opposite direction.
Might be. These are ergonomists. They are not medical experts, mm-hmm. and they are not. Basically, they're analyzing this without the workers.
I see.
So they do it offline. And afterwards they could communicate it. How they communicate to workers, mm-hmm. We would need a different visualization for sure.
I see.
So yeah.
Thank you so much
for them.
Let's go ahead and thank our speaker again. Great, you can go ahead and set up. While she's setting up, I wanted to congratulate Catalina and co-authors for their honorable mention in the Best Paper Award. So can we give her a round of applause for receiving that?
Hopefully the applause continues after the presentation as well.
Excellent. So here we have Catalina, and she's going to be telling us about traffic viz. Go ahead and take it away when you're ready.
Okay, great. Thank you everyone for coming today. I'm excited to present to you Traffic Viz, Visualizing Organized Activity in Spatiotemporal Patterns for Detecting and Labeling Human Trafficking. My name is Catalina, and I've done this work in collaboration with all of my wonderful co-authors here on the screen. So we're going to get started by explaining some domain knowledge behind human trafficking and then explain what Traffic Viz actually does. So human trafficking is incredibly pervasive, affecting about 4.8 million people worldwide. And the majority of these victims are advertised online on escort websites among many at-will sex workers doing this work of their own free will. So if we'd like to be able to find trafficking victims so we can get them the help that they need, we need to be able to separate ads representing trafficking victims from ads with at-will sex workers. So how do we do that? Well, there's some insight that can help us here about the traffickers that traffic victims. So firstly, traffickers post the ad content for the majority of the victims. Victims aren't writing the ads themselves. And secondly, traffickers use templates to advertise multiple victims. They're kind of lazy, so they copy and paste the same ad over and over again and just change the victim-specific information, which is a small percentage of the total ad. So using this insight, what we can do, and what we did do in some previous work, was crawl a bunch of these escort ads from the web and organize them into what we call microclusters, which are just small clusters of ads based on text that are highly similar to each other. So that's all in good, we're done. Each of these microclusters is a human trafficking case and it's over, right? Well, I wouldn't be here if that's true. The problem is there's other types of organized behavior in escort ads that also have high text similarity. And these include things like spam, which are fake ads posted in high volume for reasons unknown to us, scammers who are just trying to take clients' money, ask for down payment, nobody ever shows up, massage parlors that offer these kinds of services which may or may not have human trafficking activity. And finally, at-will sex workers, if they post in large volume, can sometimes show up in these microclusters as well. So the problem is we'd really like to be able to differentiate which microclusters are which, and for that, we really need labels, but we don't have any because these are crawled from the web. So we turn to our domain experts and we say, well, it would be really great if you can label these clusters for us. It turns out, if anyone's ever tried to solicit label from domain experts, that's hard. Why? Because you have all these ads from the internet and you're asking them to just check every single one and label them, and that takes forever. It's time intensive, they're busy, and they don't want to do it. So this is where an interactive visual system can come in to help, and that's what Traffic Viz does. But before we get to any visualization, I just want to talk about one thing that we do pre-Viz, which is the creation of meta-clusters. So this is what I showed you earlier. We crawl ads from the web, we make these text-based microclusters, so each of these clusters highlighted in the white boxes. But then we notice that sometimes there are traffickers that will change their template over time because they, for whatever reason, but you can tell it's the same person because they use the same contact information. So if we look at these microclusters and we observe the different pieces of metadata they use, like the phone numbers, the emails, the images, and the social media account handles, we can actually connect these text-based microclusters into larger metaclusters, which show longer behavior over a longer period of time in case they did change their template. And this resulting metacluster is what we will visualize to domain experts. So without further ado, this is what Traffic Viz actually looks like. There are 5 main panels to look at. The first of which is the microcluster panel. So here the horizontal axis represents time, and each row represents a microcluster that's within this metacluster being visualized. And we're showing the posting activity, where a darker color here means there were more ads posted on that day. There's also a drop-down where they can pick a subset of microclusters to inspect, which we'll get back to in a second, just remember it's there. The next is the metadata panel, where they can find spikes of metadata usage over time. So here in particular, we see that in summer of 2019, there were a lot of images posted, probably more than an individual sex worker could have posted on their own. Then the third panel shows the geographical spread of posts. This is called the map panel. So here we can see that we have a nationally spread activity as opposed to what we sometimes see as regional or just in one area. And then experts will spend the majority of their time actually looking at the text of the ads. So reading this text is actually not important, and you might not want to because it's explicit. But the idea here is before selecting a microcluster with that dropdown I alluded to earlier, you see the template for a microcluster. So basically what it generally looks like. Once you select a microcluster, you can look at the individual ads within them, and the highlights here represent places where there are insertions, substitutions, deletions, etc., that the individual ad is different from the template that you would have seen before selecting. And then finally, with all of this information, an expert can label for each behavior a metacluster on a 5-point Likert scale, where 1 means that it was very unlikely they exhibit that particular behavior, and 5 means the metacluster is very likely. And then they move on to the next metacluster. So Traffic Viz was developed through 9 months of participatory design with 3 main design considerations. The first of which is to make sure we provide the big picture of the metacluster while still allowing experts to drill down into microclusters as needed, which the microcluster panel has handled pretty well for us. The second consideration is to support complex multimodal data. So here we have free text, we have time series, we have geographic data, and the combination of the map, timeline, and text panels handle making sure that experts can see all of this information at once. And then finally, we wanted to make sure that this is usable for many types of experts. Possible experts that can use this include criminologists that may have a strong statistical background, or maybe volunteers that don't. And so making sure that the interface is understandable for a wide variety of people is very important. And this guided the entire design of the interface, but in particular, we had a very simple labeling task that was easy to understand. So we evaluated Traffic Viz with 4 experts. 2 of them are from Marinus Analytics, a Pittsburgh-based startup that works to fight human trafficking that we collaborate with. 1 is a criminologist, and 1 is a previous human trafficking survivor. So we asked these experts in a 1-hour Think Aloud interview to label 10 metaclusters and just give us our feedback as they were labeling the metaclusters and then also afterwards. And from this, we solicited 6 design lessons. The first of which is that the metaclustering was really helpful. Experts liked the ability to look at the metacluster and then select some microclusters to be able to drill down into them. So for example here, before selecting this microcluster C1, they see the template text, which is what you're seeing on the top. And then after selecting one, they see the individual ad with the highlighted differences. Secondly, text was the most important feature. It's what people looked at immediately when they switched to a new metacluster. So one person said they're looking for the keywords they usually see, which often fell into certain ethnicities, the number of people being advertised, or whether high-risk services were offered. The third lesson was that while metadata was secondary, it was still useful. So one person said, since there are multiple ads a day, this is likely not an individual escort. The fourth lesson was that this was accessible to a wide variety of audiences. So one expert said that this would really help investigators retrace their steps from jury or prosecution during testimony, adding to explainability and justification for why that individual is being indicted or targeted. We didn't actually get anyone from the criminal justice system in our feedback, but this would be an interesting direction in which to take Traffic Viz in the future. The fifth was that the experts thought the interface was well designed, they liked the layout, and they particularly liked that it was all in one. There wasn't a lot of scrolling, and they could see all the information at once. And this final lesson is time savings, and this one is really, really important for us here because this is what caused us to design Traffic Viz in the first place. Nobody wanted to label these ads manually. So one expert said it would take 20 to 30 minutes per cluster, and that this is a huge advantage the way things are currently done. So here I'm showing the labeling times for each expert on each metacluster. On average, it took 2 minutes and 36 seconds for someone to label a metacluster while speaking aloud to the interviewer, which is an order of magnitude faster than the estimated time it would have taken. And we didn't ask them to manually do that because they wouldn't have done it anyway. So for next steps, we would like to incorporate more types of data, like images and social media data. And we would also like to label more of these metaclusters, like this, for example, trafficking, spam, and scam here, so we have more than just 10 metaclusters. And we're working with domain experts to do that. So to finalize, we have 3 main contributions of Traffic Viz. The first is that this is high impact. This is the first known labeling system for trafficking. The second is that it enables label generation, which allows us to use these labels for evaluation and other downstream tasks. And finally, this provides a huge time savings over manual labeling to the point where we're actually able to solicit these labels from experts. So with all that being said, I would like to thank everyone for listening, and I'm happy to take any questions.
Excellent. Thank you for that. We have a few questions on Slido. First one from Elsie. How might you change the design of the human trafficking dashboard based on feedback from the experts?
Yeah, so throughout the 9 months of feedback that we got from experts, we had actually originally had a node link diagram showing some graph layouts that ended up being too confusing for a lot of experts. And there are a lot of, on this microcluster panel, how it looked like over time, this changed quite a bit. So that was a big element. In terms of the feedback we got after soliciting evaluation from the 4 experts, I think the biggest thing would be to include more granular data. That was what we saw, especially on images. But we don't actually have access to the images themselves, just the IDs for now, and that's why they weren't included.
Excellent. One more quick question. How did the labels from experts correlate? Did all of them label the cluster similarly?
Yeah, that's a great question. So it wasn't included here in the presentation, but they're actually, you can check that out in the paper. They didn't always match up. There were certain clusters that seemed easier to label than others. And some of them, it ended up that we didn't have a clear label for them, 2 out of the 10. So in the future, we were thinking to maybe have the experts discuss afterwards and try to come to a consensus.
Excellent. Thank you so much. Let's thank our speaker again. We're getting great questions on Slido, and people are upvoting them, which is awesome. So if you do have a pressing question, I recommend putting it in Slido, and then we can kind of let those be filtered up. All right, the next talk we have is from Namal. Go ahead and take it away.
Hello everyone, I'm Naimul Haq, a PhD student at University of Maryland, College Park. I am very happy to share our work, Outcome Explorer, a causality-guided interactive visual interface for interpretable algorithmic decision making. This work was part of my master's at Stony Brook University. My co-author and mentor is Klaus Muller from Stony Brook University. In recent years, algorithmic and automated decision-making systems have been deployed in many critical applications areas. It has been shown, however, that these systems can exhibit discriminatory and biased behaviors. It is thus imperative to create mechanisms by which humans can interpret and investigate these automated decision-making processes. Explainable AI has emerged to address this issue by inventing mechanisms to explain algorithmic decisions. For example, Shape can identify and visualize feature importance for a classification task. A dominant trend in XI systems is that they tend to support the need for model developers. Non-expert users who do not possess any machine learning background are not typically supported. However, non-expert users are the recipient of algorithmic decisions, and hence they have the right to explanation. At the same time, there are needs to devise models that are interpretable rather than black boxes. In this paper, we propose Outcome Explorer, an interactive tool where non-expert users can directly interact with an interpretable model and receive algorithmic decisions. To design Outcome Explorer, we adopted a 2-module design. The first module is the model creation module. Using this module, an expert user creates a causal model interactively. The interpretation module can then be used by both expert and non-expert users to understand and verify the decision-making process of the model. Let's see how an expert user, such as a machine learning developer, can create a causal model using our model creation module. The developer starts by uploading a housing dataset in the interface. The developer can then use an automated algorithm to search for a causal network. The developer can then refine this initial model. For example, he can direct an undirected edge and evaluate the model fit measures and prediction accuracy. Similarly, he can remove spurious relations from the causal model. Once the model is created, both expert and non-expert users can interact with the model in the interpretation module. In this view, the network is laid out in a left to right fashion. So let's see how a non-expert users can use this interface. Suppose Emily wants to buy a new house. She can use this interface for understanding how different factors affect housing prices in neighborhoods. She starts by putting values in the variables and seeing how that affects the outcome. She notices once she sets an internal node to a value, its incoming edges become blurred. She understood that if, for example, she knew the property tax of an area, there is no need to estimate it from other factors. While changing, she can also see which configurations are common and which are not in the realism meter. Let's look at a little bit more details about this meter next. We introduced this realism meter to allow users to determine how common their profile is compared to the existing population in the dataset. We anticipated that while changing values, a non-expert users may create a profile that may not be plausible or at least rare in terms of the existing dataset that we have in our database. To notify users about that, we trained a Gaussian mixture model on the training data, and we can then calculate any data points probability of coming from the distribution and visualize that on a linear scale such as the ones shown in the pictures. Going back to our original demo now, suppose Emily found the perfect neighborhood, but the price is too high. She wants to decrease the price while changing as little as possible from the perfect neighborhood. To do so, she can create a new orange profile which is exactly the same as the green one. She can then iteratively change the orange profile to decrease the price while keeping the original green profile static. In this way, a non-expert user can perform what-if analysis in our interface. Similarly, Emily can compare the housing configuration with an existing neighborhood from the database. To evaluate Outcome Explorer, at first we conducted Think Aloud sessions with 3 machine learning developers. Their feedback suggests Outcome Explorer is comprehensive and easy to use. It is engaging and thought-provoking. They do mention that it requires prior knowledge to create the causal model, and participants also suggested to add disclaimers in the interface that the relations in our interface are not correlations, rather they are causally related. We then conducted a user study with 18 non-expert users to assess the effectiveness of Outcome Explorer. The study included 2 conditions. The first one is Outcome Explorer with only the causal model and other features hidden. And the second condition is Shape, that uses feature importance to approximate and explain the causal model. Notice that the external nodes cannot impact the internal nodes in a causal model once the internal nodes are set to values. We refer to these variables as non-impacting variables. Notice also that Outcome Explorer visualizes this mechanism, but Shape does not. We provided participants with an initial variable configuration and outcome. We then asked them to reach a target outcome with minimum changes to the variable configuration. In a sense, this task is same as the one performed by our non-expert users, Emily. And in this way, it is also similar as to perform an what-if analysis. We calculated the number of changes participants made to the non-impacting variable, and we noticed that the Outcome Explorer significantly reduced the number of changes for the non-impacting variables. However, the total number of changes was similar for both conditions. Thus, even though participants understood which features to change in Outcome Explorer, that did not lead to overall improved performance in the exploration process. Finally, from the subjective measures, we found Outcome Explorer is easy to use and understand. In summary, we have presented Outcome Explorer, an interactive interface for algorithmic decision making that both experts and non-experts can use. We show that it is possible to support both groups in a single system. We also show that causal model is interpretable and easy to understand. We found that improved model understanding may not lead to improved efficiency, that these two notions are not necessarily linearly related. We believe our design can be extended to algorithmic fairness since causality and counterfactuals are useful concepts in fairness research. For example, we can validate how changing the gender affects the outcome. In the future, we aim to increase the scalability of our system and extend the supported models. And with that, I would like to thank you everyone, and I'm happy to take questions.
All right, thank you for that. What questions do we have for our speaker? Coming up? Yeah. Okay, you can come up.
This way everyone can hear. Hi there. I posted something on Slido, but I think it's gotten to the bottom of the list here. The realism meter that you have there is really, really neat. But does it stay in the common section so long as there's a data point that matches the criteria that are set? Or does the likelihood of each feature help to define the range that moves around?
Can you repeat the question a bit? Sorry.
Sure. So I'm talking about that realism meter.
Right.
Does it work off of the individual, like if there is a data point that matches the criteria that are set by the user, or is it based on the likelihood of those different features?
Yeah, it's sort of based on the likelihood of how likely the configuration you are putting in the interface is based on what we have in the training data set. So you are open to use any configuration, but we wanted to notify users that the configuration you are obtaining may not be very common, at least in the existing database, but you're free to use that. Thank you for the question.
So this one is from online. How common is defined in the realism meter? How do you define common?
Yep. So as I mentioned, it is actually a likelihood. So if I go back a little bit, so it's actually a probability distribution. So the scale is from 0 to 1, where 0 is rare and 1 is common. And then 0.5 is the moderately common.
Excellent. Thank you so much. Let's thank our speaker again.
Thank you all.
Okay, the next presentation up is a virtual video. So we can probably...
An interactive video tool to support direction selection. Hello everyone, welcome to my VIS presentation. NetCamLens, an interactive video tool to support direction selection in interdisciplinary experimental research of medicinal chemistry. I'm Chu Hanshi from the Hong Kong University of Science and Technology. My collaborators are Fei Nie, Yicheng Hu, and Yide Xu, and this paper was advised by Professor Lei Chen, Xiaozhen Ma, and Qiong Luo. Interdisciplinary experimental science refers to branches of knowledge that integrate the data, methods, and theories from different scientific backgrounds. and employ experiments as the key research approach. In these disciplines, identifying what research direction will be feasible and promising is usually the first step of the entire research process. Given that such research process is often time-consuming and resource-intensive, a right research direction selection in the initial stage of scientific inquiry is rather essential for researchers. But research direction selection in interdisciplinary experimental science is not an easy task. First, researchers often need to integrate large-scale, heterogeneous data from all related disciplines to evaluate candidate directions from both theoretical and practical perspectives. However, existing scientific literature and analytic tools often focus on tasks like document organization rather than helping balance the considerations from both science and strategy aspects and supporting decision-making in the research process. Second, existing methods for organizing data from scientific literature may not meet the data integration needs of interdisciplinary experimental science fields. For example, medicinal chemists commonly organize literature by the chemical structures proposed in the paper, where documents are conventionally grouped and indexed by keywords, author networks, or citation links. Lastly, when inspecting a candidate research direction, individual researchers or research groups may have different concerns. Thus, it is challenging for researchers to estimate the feasibility and difficulties of future experimental testing stemming from their decisions. In this paper, we selected medicinal chemistry as a case to explore how a scientific literature analytic system helps address the aforementioned challenges. Medicinal chemistry is a scientific discipline at the intersection of chemistry, pharmacology, and clinical pharmacy. In medicinal chemistry, researchers need to first select a particular drug target and then design and test out drug compounds against it. Therefore, in medicinal chemistry, research direction selection is drug target selection. So we proposed an interactive visual tool, MedChemLens, to support the identification of a drug target that is most likely to lead to a promising research path. MedChemLens incorporates 5 views and integrates relevant literature and data from the 3 related disciplines. In the drug target search view, users can search candidate drug targets of interest and inspect their 2D structures. The signaling pathway view visualizes the signaling pathway of each input drug target with respect to other targets in a tree format, and the nodes representing the targets searched by the user are highlighted for easily locating. This view can help users understand the interactions between the candidate targets and remind users of other drug targets that may be overlooked by them. In the candidate target collection, remind users of other drug targets that may be overlooked in the candidate target collection. For example, we can notice from this view that HER2 is an upstream target similar to EGFR and ALK, but is missed in the candidate target collection. In the publication trend view, the temporal changes in the number of publications related to each candidate drug target are displayed. Users can understand the research trend and the evolution of each candidate's popularity over time from this view. The overview uses a tabular design to provide an overall picture of the drug compound design related to different molecular features in different disciplines. Specifically, each row in the overview associates with a candidate drug target and corresponds with the candidate entry in the drug target search view. Each column represents a molecular feature. The chemistry-related, pharmacology-related, and clinical pharmacy-related columns are colored in red, blue, and orange themes respectively. These columns are arranged from left to right following the drug discovery process to show the research progress of the drug target. As for each cell, the background color denotes the number of publications or studies focusing on the corresponding molecular feature. Besides the background color, we use line charts to display the distributions of each reported feature value in each corresponding cell. This summarizes the performance of related work on a molecular feature and also implies the research potential, value, and difficulty of a drug target. For instance, we can notice that the drug compounds against KRAS achieve better SC50 than those against ST83, though there are more related works against ST83. This suggests that improving the potency of ST83 may be challenging. The detail will represent the research landscape of the existing works about a particular drug target in each discipline. It helps users integrate research data of the drug compounds across disciplines and compare the detailed drug compound research progress of the candidate targets. Specifically, it consists of 3 different panels corresponding to the 3 disciplines. The chemistry panel realized chemistry publications that proposed new drug compounds. Each publication is projected as a circular glyph. The length of the outer ring denotes the length of the synthesis route of the drug compounds. The size of the inner core encodes the total number of drug compounds proposed by the publication, and the distance between each pair of glyphs indicates the structural similarity between their drug compounds. The pharmacology panel displays the molecular features of each drug compound concerned in pharmacological testings. It contains 2 heat maps corresponding to the in vitro and in vivo assays. In each heat map, each column represents a molecular feature, and each row corresponds to a drug compound proposed by a publication in the chemistry panel. The feature value is encoded as a sequential color scale. The clinical pharmacy panel incorporates a sampling diagram to show the clinical study information of the drug compounds. Each section in the sampling diagram represents a drug compound and consists of 9 subsections corresponding to 9 stages of clinical studies. We construct our system as this pipeline shown. The pipeline could first automatically collect related publication data from publisher sites, and then extract molecular features from the publications based on a BERT model. Also, the chemical structural similarity and the synthesis route lengths are calculated based on the smells of the drug compounds, which is a line notation for describing chemical structures in textual strings. To evaluate the effectiveness of our proposed system, MedChemLens, we conducted a within-subject study with 16 chemical researchers. A restricted online search was used as the baseline in the control condition, and participants were allowed to use MedChemLens only in the experiment condition. The results show that, compared with the control condition, participants in the experiment condition reported faster search, better informed selections, higher confidence in their selections, and lower cognitive load. In summary, we contribute an interactive visual tool, MedChemLens, to support medicinal chemists in selecting drug targets. It integrates information from 3 different disciplines and organizes scholarly documentation following the practice of each discipline. A within-subject study demonstrated the effectiveness of MedChemLens. It helped users analyze relevant literature to select research directions. That's all for my presentation. Thanks for your listening and welcome questions.
All right. Thank you so much for that. We have a question on Slido. How can the signal pathway view help drug target selection process? Can you please give more details about that? If you're able to hear me.
Yes. Sure. Can you hear me?
Yes, sounds great.
Okay. Thanks for your questions. Actually, signaling pathway contains a chain of drug targets, and medicinal chemists need to understand the interactions between the targets in a signaling pathway. Because when a drug compound binds with a drug target, it will first activate this target and then activate the downstream targets in the signaling pathway, and finally produce therapeutic effects. So if medicinal chemists decide to study a drug target, they also need to have the knowledge of its downstream drug targets, since upstream targets taking effects need to go through downstream targets. So we have this panel to show the interactions between different drug targets. Yeah.
Okay.
That's all for my answer.
That's great. Thank you so much. I think we'll need to move on to the next talk. If we can cue that up, that's also, or did you have a question? Sorry, we'll have to move on for time, but you can take it offline on Discord.
Okay, thank you.
Thank you very much.
Hello everyone, welcome to my presentation. I'm Haipen from
All right, so the next one we're queuing up is from Ha Peng, and this one is on gesture lenses.
Everyone, welcome to my presentation. I'm Haipeng Zheng from Sun Yat-sen University. The paper I'm going to present is Gesture Lens, Visual Analysis of Gestures in Presentation Videos. This is a joint work with Hong Kong University of Science and Technology and Singapore Management University. As we all know, gestures play an important role in communication and presentations. Appropriate gestures have a great influence on message delivery and audience engagement. However, it's challenging to apply appropriate gestures in daily communication and public presentations. It's hard for presentation coaches to train speakers on how to use gestures. We work closely with coaches from a professional presentation training company to improve their practice of gesture training. Analyzing presentation videos is one of the common methods they use. However, manually checking and exploring gesture usage in presentation videos is often tedious and time-consuming. Therefore, we aim to help the coaches explore and analyze gesture usage in presentation videos in an easier and convenient way. Some existing tools have been proposed to facilitate analyzing gestures in collective videos. For example, some work allows the creation of gesture annotation in videos, but it's still time-consuming by watching them one by one, let alone to explore and analyze gestures in presentation videos. Prior studies have focused on how to detect and recognize gestures automatically. They mainly focus on limit categorical gesture and cannot be easily applied to presentation videos. There have been some attempts to adopt visualization techniques to analyze collective motion data, which allows users to easily explore motion data by leveraging their own knowledge. However, these methods mainly visualize and explore motion data without considering speech content in presentation scenarios. In our work, we aim to propose an interactive visualization system that supports exploring gestures and their complex correlation with speech content. Visually analyzing the gestures from presentation video is a non-trivial task due to three major reasons. First, the dynamic nature process of human motion brings significant challenges in measuring and understanding gestures in presentation videos. Second, it's difficult to summarize and digest thousands of gestures without clearly defined categories. Third, gestures are often related to speech content. Thus, without speech content, it's hard to interpret gestures used in different presentations. To address these challenges, we propose an interactive visualization system to support the exploration of gestures used in presentation videos, as well as reviewing the relationship between gestures and speech content. Specifically, we visualize the spatial and temporal distribution of gestures, adopt cluster algorithm to group similar gestures, and explicitly show the correlation between gestures and speech content. We follow a user-centric design process and work closely with two coaches from our presentation training company for about 6 months. By presenting our prototype system to our coaches, we gather their feedback and iteratively refine the specific analytical tasks. We identify 5 analytical tasks, such as obtain a spatial and temporal summary of gestures and finding similar gestures. Our visualization system pipeline contains the data modeling phase and visual exploration phase. In the data processing phase, we utilize well-established methods to extract body key points from videos, and then conduct data processing, such as gesture space mapping and gesture distance calculation. In the visual exploration phase, Four coordinate views are provided to support gesture-based and content-based exploration. The exploration views contain three major components. A heat map in the gesture space reveals the spatial summary of gestures. Two mutually perpendicular timelines uncover the temporal distribution of gestures. A transcript area shows the corresponding speech content and gestures. We embed the original video for exploration in the video view. Users can easily refer to the video for detailed analysis. We adopt a link graph designed to show the correlation between speech content and gestures. To be specific, word phrase and gesture glyphs are projected into the 2D planes with a Disney algorithm. The corresponding gesture glyphs or word phrase are highlighted and linked with lines. The dynamic view is designed to describe gesture trajectories, which provides an easier way for users to observe and compare different trajectories of gestures. A gesture trajectory is encoded with a line and dots in the gesture space. Here I present a selective scenario and expert interview to demonstrate the effectiveness of gesture length. The illustrated scenario demonstrates how to analyze open and closed gestures in a practice video. Here I will play a demo video.
Lydia, a professional presentation coach, wants to analyze her students' practice videos and find evidence for teaching. After she selects a video, the corresponding views are shown. Firstly, Lydia shifts attention to the heat map in the gesture space to observe the spatial overview of the speaker's gestures. She finds that the speaker tends to move his hands around two sides. Further, Lydia observes the speaker uses some closed and open gestures during the presentation, which is indicated by the purple and orange lines in the two timelines. She further examines the corresponding time ranges using closed and open gestures. Lydia finds that the corresponding speech content is locked in. They cross their body when using closed gestures, while the corresponding speech content for open gestures is who work all the way in Singapore, who work all over the other sides of the world in Germany. Lydia considers that these two are good examples of closed and open gestures. Next, Lydia decides to further explore the connection between gestures and speech content in the relation view. For example, she locates the term Singapore and selects some similar terms to explore how the speaker uses gestures to express locations. The corresponding gesture glyphs are highlighted and connected. Lydia confirms that the speaker tends to move his hands away to express different locations and large areas. She further examines what speech content used for closed gestures by selecting closed gestures. Corresponding word phrases are highlighted and connected. In summary, Lydia considers that the speaker can use appropriate gestures for different speech content, especially the closed gestures and open gestures.
To further evaluate our system, we conduct a semi-structured interview with 4 domain experts. They have basic knowledge about simple visualization techniques. In general, we receive positive feedback from the experts. For example, both expert 1 and 2 appreciate the idea of using visual analytics techniques to explore gestures in presentation videos. Although experts 3 and 4 were not involved in the design process, they can quickly understand the designs after a brief introduction. They also provide some suggestions, such as comparing different gesture styles and integrating other information. Here are some discussion and limitation. For the gesture analysis, currently we mainly focus on hand movements, which can be extended to other body language in presentation videos. Also, it will be interesting to explore the correlation between gestures and other multimodal features. For scalability, it might be helpful to filter out some insignificant frames and explore other designs and strategies. For generality, our approach can be extended to analyze the gesture usage of multiple speakers and analyze other related human behaviors. For summary of this work, first, we have designed and implemented a system help users to explore gestures in presentation videos. Second, we have integrated some novel design to facilitate the exploration. Third, we have conduct evaluation to demonstrate the effectiveness of our system. Thanks for your attention. I would like to take any question. Hello everyone, welcome to my presentation. I'm Haipanzhen from Sun Yat-sen University.
All right,
The
thank you
paper
so
I'm
much.
going
We
to
have a great
present is
question
gesture length,
from Slido.
visual
What
analysis of
resolution
gestures in
do you need to
presentation
use
videos.
to obtain accurate
This
gesture
is a
patterns?
joint work with
How has your
Hong Kong
model dealt with
University of
errors
Science
or
and Technology
dissimilarities?
and Singapore Management University. As we all know, gestures plays an important role in communication and presentation.
Yeah.
Appropriate gestures have a
Hello?
great influence on message delivery
Okay,
and
thank you.
audience engagement.
Do you want to repeat it or? Okay.
Hello, can you hear me?
Hello. Yes, thank you, Haipen. This is Alexandra. So there are two questions there. First, it was about the resolution that you need to identify the gestures. And the second one is how do you model the error and how do you visualize it? For example, if there is occlusion, the skeletons are incomplete, or there are some false positives.
Thanks for your questions. For the resolution, actually we just use a high resolution about 1018 plus 1900. It's a very common high resolution. We do not try other resolution, so I think it's a good question to try other resolution to test the accuracy. And for the process, actually we after we get the video and we adopt some algorithm to detect the skeleton. And after then we conduct some algorithm to measure the similarity between different skeleton. And I think the question for incomplete skeleton, since we just place the video in front of the presenter, so we can capture all the skeleton at that time. I think for the incomplete skeleton currently we do not consider that, but I think we can add some uncertainty. I mean, encode some uncertainty in that part in our visualization system.
Okay, great. Let's thank our speaker again.
Thanks for your question. Okay.
And our last speaker bringing it home is Namal. And we are very much looking forward to this particular talk on visual concept programming.
Hello everyone, I'm back. So this is Naimul again from University of Maryland College Park. I'm very happy to share our work, Visual Concept Programming, a visual analytics approach to injecting human intelligence at scale. This work was done during my internship at Bosch Research. My collaborators include Wenbin He, Liang Go, and Liu Ren from Bosch Research, and Arvind Kumar Shekhar from Bosch Urban Automated Driving Division. The bottleneck of today's AI systems is the lack of large-scale data with low effort levels, not models. For example, to train an image segmentation model, we need fine-grained annotation on every pixel. Obtaining such fine-grained annotations on a large-scale image dataset is costly and painstaking. Moreover, once assembled, it is difficult to adjust the data to a new domain, task, or objective. It is also difficult to inject newly discovered domain knowledge into the data. Data-centric AI has recently emerged to address this issue by efficiently providing weak levels with a data programming approach. In this approach, a domain expert writes labeling rules that can be applied to a large dataset. For example, for a sentiment classification task, a text can be programmed as positive with a label function searching for positive words such as happy, excited. Many other functions can be defined and applied to a large corpus. These annotations can be used for large-scale model training. Although data programming has shown great success in the NLP domain, it is challenging for image domain because of the following reasons. First, unlike using meaningful words to program text, it is difficult to describe different scenarios between the parts and the objects in an image to build labeling functions. For example, we don't really have a set of visual vocabulary or body parts such as face, hair to describe a person. Secondly, even with a set of visual concepts, we still lack an efficient tool to explore, understand, and use concepts to program images. In this work, we propose a visual analytics approach to inject human intelligence in image data for improving data quality and model performance for downstream tasks. Let's look at the component of our framework first. The method starts with a self-supervised encoder that turns many images into a dictionary of visual concepts. A visual concept can be informally defined as a group of image segments with similar semantic meaning. This concept dictionary is a foundation to augment human cognition and inject human intelligence. Let's now look at more details at our self-supervised model. The model is trained on input images that are roughly segmented with an edge detection method. The model consists of two CNNs which use a contrastive loss functions to generate pixel embeddings. The embeddings are then grouped together to generate segments. The segments are finally grouped into concept dictionary. To generate high-level tags, all segments are fed into an image encoder. Similarly, a set of predefined tags are fed into a text encoder. The similarity between the segment embedding and the text embedding can be used for assigning a tag to a segment. We design interactive visualization to help users explore concepts and define labeling functions with the concepts. For example, a head concept plus hand plus body can form a bigger concept named person. Then we can apply these labeling functions to a large-scale images and generate weak labels for the image datasets. Note here that we can use a small set of labeling functions to program unlimited image data. Finally, we can use these weak labels to train our model to improve both performance of downstream tasks and the quality of concepts. We'll now see different views of our visual interface. First, we have the concept project and rank views to explore and identify visual concepts. The projection view visualizes the concepts in a 2D plane. The rank view visualizes the concepts in a list. It shows sample segments belonging to each concept. The two views are synced, meaning interaction with one concept in one view will highlight the concept in the other view. We use concept feature view to program the visual concept with additional features such as object size, object color, relative position, and so on. The scene view retrieves and visualizes images that matches a labeling function for verification. Finally, the rule view lists and compares different labeling functions. We evaluated our framework on two datasets with model developers, a public Pascal VOG dataset for semantic segmentation and an internal dataset for autonomous driving. For the Pascal VOG dataset, our goal is to program visual concept to improve semantic segmentation performance. The developer started with a dominant category of transportation. She first selected a concept C176 with the tag of bus. While exploring, she found that this concept also corresponds to the body of trains and cars. Then she searched other concepts and identified C90 of rails to separate the concepts. She composed a leveling function indicating that a transportation running above rails must be train. After she applied this function, she spotted some outliers. With a closer look, they are buses. It can be corrected with an additional function with a lasso selection. Similarly, she composed a leveling function for cars too. With the leveling function for transportation, the developer retrained the model and found that the model significantly improved on bus, car, and train. However, she also noticed that the overall performance has dropped. After examining performance on the classes, developer found performance for farm animals dropped a lot. So therefore, she started the second iteration by focusing on farm animals. With a similar process, the performance over cow and horse is improved with a large margin, and the overall performance has also improved. With such iterations, the developer can easily compose a leveling function and have a desirable final performance. In this case, the final performance is much better than the baseline presented in NeuroIPS in ICCB 2021. For our internal autonomous driving dataset, the model developer first applied concept for scenario creation and retrieval. For example, to create the scenario, she first selected the person and the traffic concepts and constrained them to be nearby. Then they can search and retrieve many such images like this scenario for downstream tasks, for example, like sending them for leveling. Domain expert can also create the scenarios to test the model's performance. For example, they could check the model performance over traffic light plus traffic sign scenario. They found the relative position between the traffic light and traffic signs would impact a model's performance. In conclusion, in this work, we proposed a first of its kind visual concept programming approach to inject human intelligence at scale. We show for the first time that visual concepts can enable data programming for image datasets. We expect this work could shed some lights on how to use AI-generated representations such as concepts to augment human cognition and efficiently inject knowledge into data and model. Finally, we show that using our method, we can level large image datasets, learn useful data representation, and improve downstream models. With that, I would like to thank you all, and I'm happy to take questions.
All right, this question is from Jeremy Block. Do you want to voice it aloud? Should I read it? Okay. Jeremy asks, how do you track user interactions when they are refining the model? Can you roll back to a prior version?
Yes, so the model training, so the interface is designed for the writing the leveling rules. The user, using the rule view list, they can go back to any stage at their exploration time, and they can edit the leveling function at any time.
Excellent. Okay, we have a question from Jesse. How do you ensure the label functions are well set?
Sorry?
How do you ensure the label functions are well set?
Yep. So one way to do that is we have a projection view here. So for example, okay, let me go back here. Oh, okay, it's turned off. Okay, anyway, so in the projection view, we can see which images are covered by leveling functions. For example, in the middle from the projection view, you can see which data points were covered by the leveling function, and you can see whether they are well separated or not. And then again, you have the training, and it does have like such iteration, and that's why in our case study too, we show that it requires like 10, 12 iteration, but it is still much, much better than doing a crowdsourced experiment to level a huge data set.
Excellent. Let's thank our speaker again. Thank you all. That ends our session. Hopefully we'll see you all in the next session.